Cool. All right. So if you guys remember, in your previous years of science and in chemistry, when we talk about the atomic structure, we talk about a nucleus. I'm just going to write that as N. And then we also talk about the electron shells. How many shells did we teach you guys? How many were there? There's 1, 2. How many could the first shell hold? How many could the second shell hold? Third shell, how many could that hold? 8 again. Last 4th shell. 2. So we told you. 2, 8, 8, 2. Does this ring a bell? No? That's okay. I'm going to teach you guys the real thing. All right. What's the problem with this model? It's not accurate. That's true. If I add all this up, how much is that? 20. So on the periodic table, what's 20? Calcium. Do I have elements beyond calcium? Yes. And do you remember asking your teachers, what do you do beyond calcium? Kind of. Some of you guys did, some of you guys didn't. I know my kids often ask me that, and I say, don't worry about it unless you want to take level 3 chemistry. And then they don't worry about it. So welcome, everybody. You have now come to join the special club of worrying about it. All right. When we talked about atomic theory for you guys, we've talked about shells, and we kind of treated the electrons like they were going around in an orbital, like a solar system, right? So we're like, oh, there's 2 electrons here, and they're kind of going around this orbital, and like you have that whole kind of like idea of an atom. That is incorrect. That is not how atoms look. So to kind of make things more complicated, we still have the shells and things like that. We still have the nucleus. So all that's still true. But instead of having a orbital of an electron moving around like a planet, it's more like a cloud. And the electron can exist anywhere inside of that cloud. And it kind of, the best way I could describe it is that it teleports around the cloud. So like, for example, the electron could be over here, and then it can be over here, and then it can be over here, and be over here, and be over here, and that just keeps popping around, existing in that space. So what we're actually talking about when we're talking about our orbitals and our suborbitals is that we're talking about a location where you will find the electron, and that electron is somewhere in that cloud, and it's moving sporadically around it, kind of like popping around, like teleportation. It's the best way I can kind of describe what's going on. Are you okay with that so far? Okay. We're going to start looking at the subshells, and we're going to tie it to like this model with this model. Okay. So one of the pieces of paper I have given you is I have given you some shapes. These are the shapes of the various clouds, and this is where you're going to find the various electrons. There are different shapes with different complexities. So the first shape that we have is a sphere, and we call that the S, and that's our suborbital. So within the orbital, we have a suborbital with a specific shape, and your electron is going to be somewhere in that shape. That's one shape. The second shape, and unfortunately this hasn't photocopied too well, you can't really see it, but this looks like a dung bell. And you have to remember these things are in 3 dimensions. So we're thinking about like the X, Y, and Z plane. So the second shape with our dumbbell is that the dumbbell can be going straight at you, it can be going straight up and down, or it can be going kind of like sideways like that. So that shape we call the P shape. Again, it's another suborbital. P. And then the shapes keep getting more and more complicated. Now we have the D shape, and so now they're kind of like 4 little balloons that are tied together, and they can be tied together in different orientations. We have this one, which is a weird kind of like donut in the center. But again, we're talking about 3-dimensional shapes and how we rotate those 4 kind of balloons around. So this is our D suborbital. And the last one that gets really complicated is our F1, and that has lots of different shapes and, again, different orientations. So this is our F suborbital. So obviously, as I'm going up in different complexities, and that's going to have more and more energy. Are you okay with that so far? Okay. Things to remember about these suborbitals is that each suborbital can hold 2 electrons. So there's only one S shape. It's a sphere. So regardless of how I rotate it around in the 3 dimensions, it's still the same shape. So S can hold a total of 2 electrons. P has 1, 2, 3 shapes. Each can hold 2. So that would be 6. 3 times 2. So the P suborbital can hold up to 6. All right, D has 1, 2, 3, 4, 5 different shapes, each one holding 2 electrons. So D can hold up to 10 electrons. And the last one is F. F has 1, 2, 3, 4, 5, 6, 7. 7 times 2, 14. So it just gives you an idea of how many electrons each shell can hold. Are we okay with that so far? Okay. The next thing to remember is that we are still talking about shells, and we're talking about subshells. So we're talking about, like, if I have a shell, what shapes are in there? So, like, depending on the shell, you will have different shapes. So the first shell, this inner one right here, I'm going to start taking different colors now. This inner guy right here, the first shell can only have one subshell, and that's going to be the S. So the first shell only has the one S shell. So if I have a nucleus like that, and then I had a shell going around, that is my first shell, and it's the only S1 that I have. Are we okay with that so far? And that makes sense. That's only holding 2 in that first subshell, or sorry, in that first shell, because the S subshell can only hold 2. Are we okay? Shall I keep drawing? I'm gonna add some more colors. You're gonna hate it. More colors. All right. Let's talk about subshell number 2. Or sorry, not subshell number 2. Shell number 2. So shell number 2 also has an S shell. It's a little bit further away. So this is our S. We know S holds 2. Shell inside here, also an S, also holds 2. Now the second shell has the S and the P subshells. So it has this guy and these guys. So if I was to draw, I would have like the dumbbell going up. That's one of my P's. That's a dumbbell going that way. That's another one of my P's. And then like a dumbbell going this way. I'm trying to show 3-dimensional shape on a 2-dimensional plane. So do you see it has the 3 P levels as well? So the second shell has the P that holds 6. And so we know that in total, the second shell level could have 8 electrons. So do you see where that 8 comes from now, from the 2, 8? Not really? Backtrack? Okay. Okay, so shell is like the total, like shell 2. No, it's not a circle. It's just everything that's green. Yeah. And then with the shell that's green, that's 2, there are subshells. So like there's like a layer beneath it kind of thing. So there's 4 different things that are in shell 2. It's the S layer and then 3 P layers, because the P's can exist in 3 different orientations. This purple one in the middle, that's showing shell 1. That's okay. It does look like blue on the screen. That shell that's here is representing the first shell, and the first shell only has one shape, and that's the S shape. Yep. And that's how we're getting that 2 and 8. Yes? And basically what happens, I'm not going to keep drawing it because I think it's going to be a mess and it's not going to help. Each time you go up one of these shell levels, you're going to gain a new subshell. Should I explain how that looks now? Sure. Okay. I want to also add that in this question, you never have to explain like subshells and how these work. You only have to do the electron configurations. I haven't even gotten to this point. There's just a lot of teaching I have to do in order for you to understand that, which is really ridiculous for an achieve level point. Anyway, all right, let's actually break it down so you guys can see it better. Okay, so for my first shell, I only have the S subshell. Okay, and that can hold a maximum of 2. Yeah. My second shell has an S as well. Everybody has an S. That S can hold 2. So now I'm doing a superscript. Now, since I started a new shell, I'm adding a new subshell, and I'm adding the P. P's can hold 6. All right, keep going. All right. I go to subshell number 3. 3 has the exact same thing. It has a P, it has an S. Oops, that should be a 6. But now that I've gone up a level, I'm now adding the D, 3D. And how many can the D subshell hold? 10. Up to 10 electrons. And if I went up one more to 4, same thing. And now I add F, which can have 14. 1, 2, 3, 4, 5, 6, 7. Okay. And then we can keep going. So if I look at the periodic table, F is it's a new shape. F is this shape down here. All right. Now I can keep going because I know the periodic table has more than 4 rows. If I actually looked at the periodic table and I looked at the number of rows, it would go all the way down to 7. So let's add some more. Now there's only there's only F. So when I do the other ones, I would do 5S, 5P, 6, 5P, 10, D, 5D, F, 14, 6. So this is what it would look like if you were to list out all the shells and the subshells. Nothing past F. Be too big. Okay. So that's the list of all of our shells and all the subshells in those shells. Are we okay with that so far? Yeah? Shall I keep going? You guys, okay. Yep. Okay. Cool. So let's now do the electron configurations with our little subshells. I just need to grab the periodic table. So if you guys remember, I said we can't go past calcium, but now that you guys are year 13s, you can go past calcium. What is an element you've always wanted to do the electron configuration for? That's past 20. Titanium? What's this? Titanium? Is that TI? TI? Do you want me to do TI? Titanium? Okay. So here's titanium. Okay. So if I was to do the electron configuration of titanium, the thing you have to remember is that it's not a simple fill in each shell and then move up to the next one. When you get to this point here, with the 3p, you don't go into 3D. In fact, you go into the 4s because the higher shell, even though it's further away, is a simpler shape. And so it's going to fill that first and then backtrack. Let me show you what I mean. Let me show you what I mean. All right. So titanium, we know, has the atomic number of 22. So I'm going to use that first one. 1s2. That accounts for two of my protons, two of my electrons. Okay? All right, then I'm going to go down here. I'm going to do 2s2. So that's another 1, 2. And then I'm going to go over here, and I'm going to go 2p6. So 1, 2, 3, 4, 5, 6. So I'm at 10. Agreed? Okay. I finished that one. I'm going here, and I'm going to go 3s2. So that's 1, 2. And then I'm going to go over here. That's 3p6. So that's another 1, 2, 3, 4, 5, 6. How many do I have left right now? Still more. Yeah. I was at 15, 16, 17, 18. I'm 18. And how many more do I have to do? 4. All right. So you are not supposed to go to the 3D. You are instead supposed to go to the 4S. So if we were looking at it, when it comes to filling things, you do it like this. I don't know if this helps or make it worse. So I've done this, I've done that, I've gone here, I've gone down there, I've done this, and now I'm going down to the 4S. The reason why is because even though the 4S is further away, it is a simpler shape. So it wants to fill that one up first, and then it's going to backtrack and fill the more complicated one. So I will go 4s2, 1, 2, and then I'm going to go back to 3D. How many do I have left over? That's 20. So I have 2 more, 3D, 2. It's 3D 2 because I only had 2 leftover electrons. 3D 2 because I only have 2 leftover electrons.
So you can change it from 10.
Yeah. So what I'm showing here is that I filled up these suborbitals.
Yeah. Oh.
And then at this point, I was at 20.
Yeah.
And then because this has the atomic number of 22, I only have 2 left. So in the next shell, I only have to show 2. Does that make sense? Hopefully. Sort of. All right. What was I going to say about this? I'm trying to think.
Does it have to get back to 3D or could you get it back?
It has to go back to 3D because that's the next lowest energy level. Because it won't, this is lower than 4p. So it's going to go 3D first and then 4p. And then from 4p, it'll fill the 5s before it fills the 4D.
Yeah.
So that's why we have to set up this pattern. Yeah? So if you guys remember, when you guys were learning calcium has the number of 20. So we're like 2, there's your 8, there's your next 8, there's your 2. And then we said, beyond calcium, do not worry because it's going to get really complicated. The really complicated is you're going to go back to the 3rd shell. That's why we didn't tell you guys that. Do you see why we stopped at calcium now? Okay, so calcium. 2. There's your 8. There's your next 8. So that's getting up to 18. And then your last 2, that gets you up to 20 because calcium has the atomic number of 20. And they said, don't worry after calcium. You can worry about that at level 3. You're now level 3. You now need to worry about it. So now, once you get past 20, you have to go back to the third shell. Can you imagine me trying to explain that to you in year 9? Go back to the third shell. Then go up to the fourth shell. Then go to the fifth shell. Then go back to the fourth shell. You can see how this would have been a nightmare. But now you guys know. All right. What I'm going to do is I'm going to stop at this point because I want you guys to have a chance to practice this. And then we'll talk about some of the other stuff. I do want to note that I've given you guys this to help you. So, fun fact, titanium is over here on our periodic table at 22. Do you see how, when you're filling this out, all these are full, and then the 3D, you have 1, 2. And it ends at 3D 2. So you won't be given this on the assessment. I'm sorry, this isn't something they give you on the exam, but I'm giving it to you as a visual aid to help you learn electron configuration. Yeah? The other thing I want to point out to you guys is if you want to shortcut any of your writing, you can use the noble gases. So here's titanium. The closest noble gas is argon. So what you could also write is argon in brackets, which counts up to this guy here. And then you can write 4s2, 3d2 to save yourself some time. Do you want me to backtrack to where I got that from? Okay. So here's titanium. The noble gas that comes before it is argon over here. Yep. So what I can do is I can do argon in square brackets to save myself time so I don't have to write all of this, because this all here represents argon. And then the last two things that aren't part of argon I have to represent on the end, which I can figure out with this guy over here is 4s2 and then 3d2. It's a lot of work for an achieved point, I know. All right, I'm going to let you guys have a chance just to practice this before I give you any more information, okay? In fact, what you're practicing is your homework. Now, I just want you guys to keep in mind that there's a couple of questions I need you to skip because that's what I'm going to go over in the second half of this lesson. I want you to skip anything that is an ion. So anything that's charged, you can skip it on the homework right now. And anything with chromium, Cr, or copper, Cu, you can skip because those ones are exceptions to the rule. So give you guys some time. I know, exceptions to the rules. It's just always going to happen. Some practice. Yeah. All right. So, yeah, but now you feel real good. It makes a lot of sense. Okay. I'm going to throw some more things at you. So, the first thing I'm going to throw at you is that there are 2 exceptions to the rules when it comes to the filling in of charts. And that's going to be chromium, Cr, and copper, Cu. So it just has to do with the atomic numbers that they have, and so they're going to fill in a slightly different way. I'm just trying to think which is the one that I want to do first, because there is an order to what I was doing once I find it. Okay, chromium's the first one that I want to do. Cr. Let me just get my periodic table back so I can see what the number is. All right. Chromium has the atomic number of 24. Do you guys want me to write down the incorrect answer or just jump straight to the correct answer? The incorrect first so you guys can understand? All right. So if you were to write chromium, looking at where it was on the periodic table, where did my sheet go? Here it is. Okay. So chromium is 24. So that'd be 21, 22, 23, 24. It's right over here. Like that. Now, what you would expect it to have as the number would be 1s2, 2s2, 2p6, 3s2, and then if I was keeping going on that, it should have 3p6, 4s2, and then 3d, 1, 2, 3, 4. Yeah? That's what you would expect it to be. What was I going to say? That is what you would expect it to be based off of how you would use this table, or if you were using your little swipey thing, right? This is incorrect. And that's because this is an exception to the rule. So, because of chromium's unique number, what it's going to do is it's going to take one of the electrons in the 4s suborbital, and it's actually going to put it into the 3d instead. So instead, what you should have as the correct answer is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. It can do a half-filled D shell, and it's more stable doing that than having a full 4s shell and an incomplete D shell. D shell. The reason why is because when we are looking at these suborbital shapes, each one of these suborbitals can have one electron in them instead of having to pair up. So that's the ideal reasoning behind it. So if we're looking at these shapes over here, each one of these shapes would rather be an electron by itself than an electron sharing that one shape. So when it comes to filling it, it would go 1, 2, 3, 4, 5, 6, 7, 8 is the preference. So that way it can only have its own space. So that's what that's doing here. Are we okay? All right, next one is copper, Cu. Copper has the atomic number of 29. Do you want the wrong answer again, or you just want me to go to the right answer? Just straight to the right answer? All right. So this one does something similar. It doesn't complete the 4s subshell. Instead, it promotes one of them up to the 3d subshell. So what you will have instead is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 again, and then 3d10. So again, it's more stable with a full D shell. Yeah, these are the only two exceptions. Yeah, those two are the only exceptions. Everybody else follows their rules. It's just because by chance their atomic number results in them being able to do this and are thus then more stable. Are we okay? All right. The last thing I need to tell you guys is about ions. So with ions, you have to remember that you need to add or remove electrons based off the charge. So if we have a negative ion, you're going to add electrons to whatever your count is. So if I have Br minus and Br is 35, because it's an ion, there's actually 36 electrons when you're doing your electron configuration. Does that make sense? Do you guys need to see me write that one out? Yes? You just add 1 to the number. Yeah. So if I was to write that out, I'd write that out as beryllium. In fact, if you wanted a shortcut, you could just write krypton in brackets, but I'll do it the way you want it. All right. So if I was to write this one, it would be 1s2, 2s2, 2p6, 3s2, 3p6. Where are you, boron? 4s, 2, 3d, 10. Where am I? P's. 2, 3. 3p. 3p6. Sorry, 4p6. So this is changing basically. If it was Br, it would end in a 5. Yeah. So it would be. But if it's I've added one more. Yeah. All right. With the positive ions, you are removing electrons. So you take them away. The thing you have to be careful of when you remove electrons is that you need to remove them from the furthest shell, not the last filled shell. Let me show you what I mean. Not the shell you filled last. So for example, I'm trying to think of what's a good one. What did I do? Oh, we've already done copper. So you see how this is copper here? Yeah? Actually, yeah, copper's fine. All right. So the last shell that we filled in copper should have been the 3D, correct? And so you're like, ooh, I should take, if I want to say copper 2+, I should take 2 electrons off of this guy. The answer is no, because that's not the furthest shell. The 4s shell is further away. So you should be taking it from this guy first and then the 3D. So if I was to do the copper 2 ion, I would take this one away, that's -1, and then 1 from the 3D. Yep. That's what I mean by you need to remove it from the furthest. And that's probably the answer to one of your homework questions. Yeah. So just be careful, in particular with the ions that are positively charged. When you remove those electrons, remove them from the outermost shell. In most cases, we'll be dealing with transition metal, so you should be taking them off of the 4s first. Yeah? Or if you're dealing with stuff down here, the 5s before the 4D. So the 4D and the 3D, these guys are going to be filled last, but just because they're filled last doesn't mean they're the first one to take the electrons off. You take the electrons off from the furthest location, not the one with the most energy. Cool. All right. That's all I got to tell you. Questions, concerns, comments? Are you okay? You're doing a lot of work for an achieve point. I'm really sorry. There's a lot of explanation to do that. All right. It's not an excellence point. I'm sorry. The good news is everything that I've explained to you about like this stuff, you don't actually need to explain. You just have to be able to do this. So if you can do the homework, then you're fine. All right. Let me get that stopped.